binary logistic regression with one binary predictor or one ordinal predictor in SPSS. Binary logistic regression for a predictor that is binary in SPSS. Logistic regression is a statistical test that can be performed when the outcome or the dependent variable or the response variable is binary, which means that it has two categories in it or two levels. Yes, no, have disease, doesn't have a disease, have diabetes, doesn't have a diabetes. And the second variable, which is the independent variable or the exposure variable or the explanatory variable, can be binary. Again, binary means that has two levels in it, such as the sex or the gender, male or females. To perform the binary logistic regression with a binary predictor, the outcome has to be binary and the predictor has to be binary. The objective of doing binary logistic regression is to find out whether there is a relationship or a link or association between the predictor and the outcome, and whether the predictor can predict the outcome. Here in this SPSS data sheet, I had inserted 100 cases or participants. There are two variables here, one for gender and one for heart diseases. So the first one, which is the gender, is a binary or binomial variable, have two levels in it, males or females. If I click on the variable view and click on the values for the sex, 0 is assigned for females and 1 is assigned for males. So here we have one variable which is binary or dichotomous, have yes or no, or have male or females in it. 1 for male and 0 for females. The second variable, which is heart diseases, whether you have a heart diseases or not. If we click on variable view, then in values, and the 0 value is assigned for no heart diseases and 1 is assigned for heart diseases. So here we have a variable which is binary. If I click on that icon, you can see it's coded 0 or 1. So here we have two variables. One of the variable is the outcome, which is the heart diseases, whether you can get a heart diseases or you will not get a heart diseases based on the data inserted here. So to find out whether there is association or relationship between the gender and possibility or probability of getting heart diseases, binary logistic regression can be performed. And the condition for performing that test is fulfilled, as there are two variables. One of them is the outcome, which is binary, and the other one, which is a predictor, which is also a binary. Before we start, let's check the frequency for each variable. If we click on Analyze Frequencies and then drag the sex to the variable box and the heart diseases, click on Statistics and nothing to choose from here. Let's just click on OK. Again, multiple tables are generated. The first table shows that there are 100 cases with no missing values for sex and heart diseases. For the first variable, which is the predictor, which is the sex, there are 52% of female and 48% of males. And for the heart diseases, 44% have no heart diseases and 56% have heart diseases. To perform logistic regression binary, click on Analyze, scroll down to Regression, and then scroll down and select the binary logistic regression. Reset that window, and in that window, since we know that the heart diseases is the outcome or the dependent variable, this is the variable we want to find out whether the predictor, which is the sex, which is a binary, can predict probability or possibility of having heart diseases. Drag that into the box here. Since we have here a predictor that is binary or categorical, click on categorical, drag the 6 here. Although it is just having only 2 levels in it, I'm going to set the 0 for the first, which means that male will be compared to females. Click on continue. For options, I'm going to select classification, plots, Hosmer, goodness of fit, and confidence interval for the exponential p. Click on continue, click on OK. Multiple tables are generated. The first table shows a summary for the case or cases. As shown, 100 cases, no missing values or cases. The second table is the dependent variable, which is the outcome, which is the heart diseases. As shown here, it has been given a value of 0 for no heart diseases and 1 assigned for heart diseases. And for the categorical variable coding, females are given a value of 0 and male are given as a value of 1. Moving to this table, which is variable in the equation, this is a very important table, shows here the coefficient value and the test which is used for binary logistic regression, which is called Wald test. Standard error is generated, and degree of freedom, significant p-value, and exponential p, which is the odds ratio. Moving to the section here, which is for method enter, the important table also here is the model summary. A model is generated by trying to fit the predictor into the outcome to generate a model in which the possibility of the predictor can predict the outcome. Again, looking at the R square here, which is the value here, which is 0.735. This value means that 73.5% of the variation in the outcome, which is the heart diseases, whether you have a heart disease or not, can be explained by the predictor, which is the sex, whether male or a female. So the sex or the gender of individual can explain the variation in the outcome. Jumping to the last diagram here, which is very important, as shown from this diagram, predicted probability is of the membership for HD. So we are here calculating the probability or the chances or the odds for heart diseases, possibility of heart diseases. The table here is also an important output for the interpretation of the result from the analysis, binary regression. There's a value is given here for the coefficient, the standard error, the Wald test, the degree of freedom, significant as it is less than 0.05, and 95% confidence interval for the exponential, which is the odds ratio. This is for the predictor or the variable, which is sex, and again given a value of 1. Here we are comparing the males to females. So the way to read this result or interpret this result, it shows that there is a significant association between the outcome, which is possibility of getting heart diseases, and the predictor, which is the gender of the individual. As shown here, the males have a 224.5 odds of having heart diseases compared to females. So the males had an increased chance of getting heart diseases with an odds of 224.5 related to the females. So this is the way to perform binary logistic regression with an outcome that is binary, which has 2 levels in it, and a predictor, which is binary, have also 2 levels in it, to find out whether there is a relationship between both variables and whether the predictor can predict the outcome. Binary logistic regression with an ordinal predictor in SPSS. Here in this SPSS data view, I have two variables and there are 200 cases here. Those two variables are the age, categories, and diabetes, whether you have a diabetes or no diabetes. The age category is an age that has been arranged or sorted into categories. The first category is an age of 16 to 24. The second one is 25 to 45. The third one 46 to 70. And the last one is greater than 70 years old. So this variable is categorical variable, but it is ordinal more precisely, as it has categories in it, but there is an order. 16 to 24 is the first, and then 25 to 45 is the second. So this variable is a ordinal variable. The second variable is diabetes, has only two levels in it, two categories, so it's binomial or binary variable with either yes, you have diabetes, no, you don't have diabetes. So here we have two variables, one of them is binary, the other one is ordinal. So the age category is the predictor and the diabetes is the outcome. So to find out whether the age categories can predict the outcome, which is whether you have diabetes or not, or whether increasing the classes or categories of age can increase the chances or the probability or the likelihood of getting diabetes, then binary logistic regression can be used. And since the conditions are satisfied, that we have two variables here, an outcome which is binary for diabetes and ordinal predictor which is the age categories. This logistic regression will determine whether there is association between these two variables. Before we proceed to perform the test, let's do some statistical descriptive. Click on analyze, scroll down to descriptive statistics, frequencies, reset this, drag the age categories and diabetes to the box for variables, click on OK. Multiple tables are generated. The first one shows that there are 200 cases for the age and diabetes, the two variables, no missing values here. The next table is for the age categories from the first category from 16 to 24 up to greater than 70. There are 50 cases in each category. And for diabetes, there are 119 cases of no diabetes and 81 of having diabetes. In fact, before we proceed to the test, let's look at the coding for the variables. For the first variable, which is the age categories, 0 is assigned for the first category from 16 to 24 and 3 for greater than 70. So this value here, 0, will be taken as a reference category for comparison in the logistic regression. For the outcome, which is the diabetes, 0 for no and 1 for yes. Back again to the data view here. To perform the binary logistic regression with a ordinal predictor and a binary outcome, click on analyze, scroll down to regression, select the binary logistic regression, reset this. Since the diabetes is the outcome, drag that to the dependent box here, and the age category, drag it into the box here. As shown here in this box, any variable can be dragged in, whether it's continuous variable, whether it is binary variable, whether it is ordinal variable. And since the age categories are categorical, there are 4 categories in it, drag that into this box and select the reference category, which is the first. In this case, the 0, which is 16 to 24, will be the reference category to compare to. Click on continue, then click on options. Select the classification plots. Select this goodness of fit test and confidence interval for the exponential p-value. Click on continue and then click on OK. Multiple table will be generated and a diagram at the end which shows that the predicted probability is of a membership for yes. Back again to the top here, as shown here, the first table shows the case processing summary. There are 200 cases, no missing cases. The second table is coding for the outcome, which is a diabetes, yes or no. Yes for 1, 0 for no. And the next table is for the ordinal variable with the age classes, with the frequencies and the number of cases in each category. Moving to the classification table, again shows those cases with diabetes and those without diabetes. The next table is variable in the equation. P stands for the coefficient, SE for standard error, Wald is the test used for logistic regression, degree of freedom, significant value is taken as P less than 0.05, and exponential P. The most important, in fact, section is the one start from here, in which shows that the model summary. This is an important table. This model summary, this value here, R square, is the one to look at, which says or states that or describe that 25.5% of the variation in the outcome, which is diabetes, can be explained by the age category or the ordinal variable. Moving to this section here, we need this value to be greater than 0.05, and the important table to focus on is this one, the variable in the equation. Again, this table as shown here in the section, this is the variable for age categories. The age category which is assigned a 0 value is considered as a reference, which is from 16 to 24, as not shown here. But the age 1 is for 25 to 45, age category 2 is for 46 to 70, and the last one is greater than 70. The coefficient is given for each one of them, the standard error, the degree of freedom, significance, and as shown here, all the three categories are significant, less than 0.05, and an exponential value p value is given here, and as we can see, an increasing value with increasing classes of age, getting older. And then 95% confidence interval is given for each value for the odds ratio. This exponential p is the odds ratio. And here we have two layers of determining whether there is significant or not p-value and the 95% confidence interval. From these significant, it is well shown that there is association or there is a relationship between having diabetes or not compared or relative to the predictor, which is the age category. So there is association between these two variables, and the predictor, which is the age classes, can predict the outcome, whether which is in which you probably have a diabetes or not. The way to interpret the result is that those who have an age category from 25 to 45 years old have increased likely of getting diabetes compared to the younger group. The odds ratio is 3.14. In another way, those with a category of age from 25 to 45 have an increased odds of 3.1 to get diabetes compared to the age group which is from 16 to 24. The second category, which is age cat 2, in which the age category is from 46 to 70. Again, the odds ratio is 7.3, so this one is higher than the previous one, and the third one is also higher. So there is a trend of increasing odds ratio with increased age classes. Again, for the age category 2, those with the age from 46 to 70 have an increased odds of 7.3 relative to the reference group, which is a younger group. So there is an increased chance of getting diabetes with increased age. And finally, for the individual who are greater than 70 years old, they have an increased odds of 17.11 to get diabetes compared to the younger group. So the oldest individual have a higher odds, higher probability, higher likelihood of developing diabetes compared to a younger group or younger individual. So this is the way to interpret the output from a binary logistic regression for an outcome that is binary and for a predictor that is ordinal in SPSS. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovie, R Statistic, or Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovie, R Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.